Nice. So Friday night experiments. So at COS, I don't know if you know this, there's Friday night labs where they meet and do cool stuff. It's over there in the physics lab, but we've started Friday night chemistry, and a few students have been trying to synthesize caffeine from a patent from like 1940. And in the abstract of this patent, it's talking about how World War II, actually, I don't think they even called it World War II at the time, but they're like, the current global war is restricting like the trade of like coffee, and we're not getting enough caffeine. So we patented this synthesis of caffeine so that we could just make caffeine, which is really interesting. They haven't quite synthesized it. Organic chemistry is kind of a long and slow process, especially when you're working with patents that are that old. And they're like, oh, hey, yeah, we just added a gallon of sulfuric acid to our 3-gallon flask. I don't remember. But they're talking about gallons instead of liters. They're also doing things in huge quantities. So trying to scale that down is difficult. And then there's also just like little bits of information that feel like they're missing, how long they let it sit for or things like that. So that's Friday Night Lab, and they're just experiments for fun and to get used to experimentation. This is a similar thing, except it was, I looked this up before. I think it was just Geim. He was doing these exploring these lateral ideas in this Friday Night Lab, in his Friday night experiments, where he was just trying stuff that weren't in his area of expertise. I want to do something with, I don't know what kind of, oh yeah, he was a physicist. So I'm going to do something with chemistry. He's not a chemist. He knows some chemistry, knows a lot of physics, tries to do something with that. Most of those things didn't turn into anything, but one of them did, and that was for graphene. So graphene is carbon. Do you have that? No. Basically, he took, if I'm remembering this experiment correctly, took a piece of Scotch tape onto a block of graphite. So like your pencil lead, right? That's graphite. It's made up of carbon atoms. So you took a piece of Scotch tape, put it on there, and then peel it off. And what they found was that when you peel that Scotch tape off, it only removes a single layer of carbon atoms. And that single layer of carbon atoms has some pretty crazy properties. One of them being that it's like really conductive. And it's a very strong material, and there's been a lot of talk for the last 20 or 30 years, maybe not 20 years, the last 10 years, 13 years, of how graphene and carbon nanotubes are going to change the world and how they're going to do all these crazy things. The problem is that they're really hard to make. Another place where this kind of occurs is carbon fiber. So carbon fiber is using carbon, I think a sort of graphene-like process to get really strong and light structures just made of carbon. Early experiments in exploring the structures of things used X-ray crystallography. So crystalline solids have long-range order to their atoms or molecules. They're crystals, repeating shapes, repeating order. And what you can do is you can shine X-rays through that. And we've talked about interference, and we talked about the double slit experiment. So essentially what happens when you shine X-rays through crystal structures is the distances between the atoms in those crystal structures are the same wavelength or the same distance as the wavelength of X-rays. And so the X-rays will diffract through those slits and create interference patterns that, if you work it backwards, tell you what the structure of the crystal is. So because of the light interfering with itself as it passes through these, yeah, you can determine the structure of the things that you're shining the X-rays through. So like for this crystalline solid, this is a hexagonal crystal lattice. And shining a light through that, you'll get some sort of, right, there's patterns to this crystal lattice. And there's patterns to the light that shines through this crystal structure. So those atoms, right, have spacings about 10 to the 2 picometers, so about 100 picometers, which is about the wavelength of X-rays. So if you shine any light through any slit, if the wavelength matches or is about the same size as that slit, it'll cause that diffraction. And then if you have a bunch of slits that are close to each other, the diffracted light on the opposite side starts to interfere and creates those interference patterns. So two waves in phase will have constructive interference. If the difference in the path lengths 2a is an integral number of the wavelengths, I'm going to be real honest, I don't really want to go into the math here. So don't worry too much about the math. But the way that the light shines through these here is if it's shining through at the right angle, you'll get these constructive interference patterns. So typically, the angle that produces the constructive interference is measured, and then the distance between the atomic layers can be calculated using this formula. X-ray crystallography is used to determine the structures of simple atomic lattices, proteins, DNA, all kinds of other things. If you can get it to solidify into a crystal structure, you can use X-ray crystallography. Sometimes it's harder, right? Don't care about the math. This last chapter is decently light. The hardest part I think about this is going to be unit cells and basic structures. So these crystalline lattices, which are the regular arrangement of atoms within a crystalline solid, because particles are combining to minimize their energy. We talked about lattice energy, where if you took the sort of bond energies of ionic compounds coming together, it doesn't add up to what the actual enthalpy would be. And that extra enthalpy is the lattice energy. Now, to talk about crystalline lattices, we've got these repeating structures. So the easiest way to talk about any crystal lattice is to try and boil it down to the simplest piece of that crystal lattice. So if I can draw a square or a box, for example, around any set of those atoms, then I can talk about this one unit. And if I have more of that substance, I'm just stacking units together because each unit represents the repeating pattern of the whole structure. So the unit cell is that smallest simple unit. And for however big the crystal structure could be, you're just sticking these unit cells together to make that whole lattice, or breaking it down to a single piece. So in a two-dimensional unit cell like this, we've got circles. Those represent our lattice points, which will be our atoms or ions or whatever atomic solid, could be a molecule. And then the dark square here is the unit cell for this two-dimensional lattice. So I just wanted you to take a minute or so, look at this, try and think about how this is representing this repeating pattern that could be, like I can shift it over here, and then shift it down here, then shift it over here, and I can keep repeating that, and it's the same pattern over and over and over again. And actually, before we even move on anymore, how many total circles are contained within this box? It's more than one per box because we got the corners there. Yeah, so this one adds up to 2 because in each corner, we get 1/4 of a circle. So yeah, and we've got 4 corners. If every corner has a quarter, then we get another circle out of that. So there would be 2 circles per unit cell here. So keep this in mind because it gets a little bit harder to visualize when we blow this up into 3 dimensions. So we got 7 fundamental types of unit cells. For cubic unit cells, that's this first one, we're going to have equal edge lengths and 90-degree angles at all of their intersections. And we're going to talk about just cubic ones. We're only going to talk about 3. We won't get into, actually mention hexagonal, but we're only really going to dive into the cubic unit cells. So for the unit cells that we're going to look at, each atom in any one structure is identical to the other atoms in that structure. So we're looking at really an atomic solid that's made up of all the same type of atoms. There's going to be different colors, and that's just to help you visualize things inside the unit cell. And then there's a couple different metrics that we want to look at for these two. One of them is the coordination number, which the coordination number is just for if you looked at any individual atom in the lattice, really, any atom in the lattice, how many adjacent atoms does it have? How many atoms is it touching? So that's our coordination number. And then packing efficiency. So since we're talking about atoms, and we're assuming that all of the atoms are perfect, spheres don't pack together perfectly, right? Even if you took a bunch of marbles and put them in a box, there's going to be space in between those marbles. And so packing efficiency is how much of the actual space the atoms will take up. And there's always going to be some left over. It's going to be inefficiency. And then as we increase our coordination number, we're going to get greater packing efficiency. All right. So this is the broad overview. These are the ones all the ones we're going to cover. So again, I said there are going to be some different colors going on here. So in this body-centered cubic, that's 5. Actually, sorry, not 5. Those are all atoms of the same type. The yellow one is just in the center. And then for a face-centered cubic, again, these are all the same types of atoms. And we'll look at each of these more in depth. Probably what I'd do on the exam is I'd probably give you this rather than have you memorize packing efficiency. Okay. So for the simple cubic unit cell, we're going to be doing some mathematical gymnastics here to calculate things like packing efficiency. So when we take the simple cubic unit cell, can you see how this is like that original one that we had? Actually, let me do this. With the power of modern technology, copy paste. So the simple cubic unit cell is pretty much what we're looking at if we're looking at the top of this sort of 2D lattice cell. Now, instead of there being space in between these circles, each of these circles is taking up the whole space. Or actually, oh, no, wait, this is slightly different. I have to draw it. So this is the simple cubic unit. So each of these corners of the unit is in the center of an atom. And so we get 1/4 of an atom in each, or not even 1/4, sorry, 1/8 of an atom in each corner. And since there's 8 corners to the cube, we end up getting a 1 whole atom in our simple cubic unit cell. And then along each side, because we have 2 atoms sitting up next to each other, we could describe the length of this simple cubic unit cell as being 2r, right? So it's 2 radii of that atom that makes up the length of one side. So if we wanted the volume of the whole cube, we could take the length would be cubed. Or we could say, so if we cube the length, then it would be 2r cubed, would be the whole unit cell, yeah? You could also say that, and in this case it would be easier. In some of the other ones, it's easier to continue to talk about the radius in terms of how many radii there are. But yes, you could just talk about it as the diameter. So if we blow this out, you can see the coordination number here is 6. So if I look at this atom that's in the middle of that gray blur, there's 1, 2, 3, 4, 5, 6 atoms that it's touching. Now here they're not touching because it's been expanded out so we can see everything. But you can also visualize this, like for this one on the corner, it's touching, touching ones that we can see are these 1, 2, and 3. But if this was repeated, there'd be another sphere out here, another one on top, and then another one that's closer to us in the plane. And so when we chop out that cube, it gives us this shape. And the packing efficiency for that, only 52%. So just over half of the space of that cube is actually being taken up by the atom. Oh yeah, okay. I didn't do this one. This is the two-dimensional lattice, though, that's most similar to that simple cubic unit. So again, we've got a square, and in each of the corners of these squares, we've got a quarter of a circle. And what's the area of a circle? 2 pi r squared. So 2 pi r squared. And so what's the length of one of these sides of the square? The whole side is 2 halves of a circle. So it'd be 2r. This is a quarter of the area, but it's half the diameter. Or, yeah, that's half the diameter, so this is half the diameter. Yeah. Pi r squared. Thank you. Pi r squared. So this would be the area of one circle, and then the area of the square, the whole square, would be 2r squared, because 2r gives us the length of one side, and then if we square the length of one side, we get the area of the square. So to calculate the packing efficiency, it's the area of the circles in the thing. Since we have 4 quarters, then it's just one circle that would take up that space. And then we divide that by the area of the unit cell. And then what happens here is we get pi r squared over 4r squared. The r squared's canceled, so pi divided by 4. Calculator. Should be 52. No, it'll be different because it's not a volume. Give me like 70-something%. 78. So this would be 70. This comes out to 0.7854. So that's 78 point, we'll do 54%. Who knows what our significant figures is there, because we don't have any actual measurements. So that's how you calculate the packing efficiency, which of course becomes trickier when you move into 3 dimensions. But it's the same concept. So this is the body-centered cubic unit cell. The biggest difference is now, instead of our unit cell having nothing in the middle, we have a whole atom in the middle. And this unit cell is larger than the previous unit cell, because each of these is still 1/8 of an atom. So if we have 4 corners, which are the 8 corners, which are all 1/8 of the volume of an atom, and we have 1 atom in the center, how many atoms fit inside the body-centered cubic? 2. It's the one in the center and then the corners. So we'll have 2 atoms per unit. Oh, and then all of this math is to calculate the length of one side of this unit cell. And the trick that they're using here is that this length plus this diagonal, and then this diagonal across from the bottom left up to the top right there, which goes straight through the center of that central atom, forms a right triangle. And so we can use Pythagorean theorem. So c squared equals b squared plus L squared, because we want to know, or because we know what this distance is here. Because we have the entire radius, or the entire diameter of that central atom, plus 1 r there and another r here. So that's where this 4r comes from. So C for this triangle, C equals 4r. So we plug that in for this. And then on this diagonal, if we want to know what that diagonal's length is, that's one length. That's two lengths of the unit cell. So length squared plus length squared is going to be b squared. So we get 2l squared. That's b squared, and that's why that gets put in here. And then we just solve for L. And all that really does is it puts L into terms of the radius of each of the atoms. That will all simplify down, and we get L equals 4r divided by the square root of 3. Does that make sense? Did everybody follow that? So if we have the length of one of the sides, then we can calculate how much of this space is filled. And we could calculate the packing efficiency. And actually, let me just, all right, so there's 2 atoms per unit cell. So 4/3 pi r cubed is the area of the volume of one circle or one sphere. So we'll have 2 spheres, and then that'll be divided by this length that we calculated, cubed. So if we cube one length of the cube, that gives us the volume of the cube. So 4 over the square root of 3 cubed. And this will equal, I missed the r, huh? 4r. The r's end up canceling out. So regardless of the radius, the packing efficiency is always the same. But this will equal 68%. So only 68% of that volume is taken up by the spheres. And we've moved from a coordination number of 6 up to a coordination number of 8. So now each atom is directly touching 8 other atoms. So if you think about it, it makes sense. As our coordination number increases, that means that our atoms are touching more atoms, which means that there's less space between all the atoms, which means it packs more efficiently. Okay, so if an atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell, what is the volume of the unit cell in centimeters cubed? And this is why I would just give you the chart. Because all we really need here, if we want the volume, then we need to calculate the length, which was 4r divided by the square root of 3. So our radius is 138 picometers. And let's say this, whenever you're doing these kinds of things, because we're going to eventually take this and cube it, convert picometers to centimeters first. So it goes, let's see, micrometers, nanometers, and then picometers. And this is 10 to the minus 6 meters. This is 10 to the minus 9 meters. This is 10 to the minus 12 meters. So 138 picometers, 10 to the negative 12 meters. So 1 picometer. And then we want 10 to the negative 2 meters is 1 centimeter. This will be 138 times 10 to the negative 10 centimeters. So multiply by 4, divide by the square root of 3. And then cube it. So this is 3.24 times 10 to the negative 23 centimeters cubed. And really the only thing involved here was converting picometers to centimeters and then knowing what the formula is. it's just a lot of, it really is just a bunch of geometry. Pretty clever geometry. Yeah. Oh, because it asks for the units, volume of the unit cell in centimeters cubed. So if you don't do it and you get your answer in picometers cubed, then you've got to do this, basically do this whole conversion 3 times. So it's easier to do that first than calculate the volume. All right, the most efficient packing or unit cell that we're going to talk about is the face-centered unit cell. Again, just using some algebra here and some geometry to figure out what the length of one of the sides is. So face-centered cubic is different from the body-centered cubic, because in the body-centered, there's a whole body in the center. And in the face-centered cubic, now we've got essentially a whole, or a half an atom in each face of the cube. So there's one here and then on the opposite side. And so since we can see these 3, there are going to be 3 other ones. And then we still have an eighth of the volume of a sphere in each of the corners. So how many whole atoms fit in the face-centered cubic? Four. So each of these ones in the face, since there's 6 faces, that's going to be 3. And then we get 1 more for the ones in the corner. So we'll have 4 atoms per unit cell. And then to solve for the length here, it's a little bit simpler because we don't need to do that whole triangle through the center. We can just say that the length of B, that diagonal, which is going to be, again, 4R. So we had a half an R, or well, 1R, 1R, and then 1 diameter, which is 2R. So B is 4R, and then the length of 2 of those legs of the right triangle are both L. So that gets 2L squared, so plugging in here. And then some algebra means that L is 2 times the square root of 2 times R. So for this face-centered cubic, I've got a packing efficiency of 74%. And then again, we get 4 atoms, and now our coordination number has jumped up to 12. So coordination number starts at 6, goes to 8, then 12. Atoms per unit goes from 1 to 2 to 4. Packing efficiency goes from 52 to 68 to 74%. Yeah, I guess we can just work through this whole thing. Let's think about conceptually what we need to do first for this problem. So we're asked to calculate the density of solid crystalline chromium in grams per centimeter cubed. And we're only given the radius of a chromium atom. Huh? Oh yeah, you mean the molar mass? Oh nice, it's just 52 on there. So that's 52.00 grams per mole. Cool. How many, so this is body-centered cubic. So it's the second one that we talked about. I'll just scroll up here. All right, so we can get 2 atoms per unit cell. So that means in every unit cell, and again, we can take an infinite number of unit cells and stack them together, and that'll create the crystal lattice of chromium for any size. In each of those units, though, we're going to have 2 chromium atoms. So we're going to have 2 chromium per unit cell. So remember, density is mass per centimeter cubed. So how much mass per centimeter cubed of chromium in each of these unit cells. So what should we do next? Yeah, that's a great idea. I'll write it out, but I think so. 125 picometers, 10 to the negative 12. This is going to be 125 times 10 to the negative 10 centimeters. This is one of those times where it's easier to leave it as just 125 rather than try and move the decimal around so that we get 1.25. And then what? Well, that's the radius. So we can calculate though. So we're assuming that the chromium atoms are all spheres. So we can calculate the volume of the sphere. 4/3 pi, this will be r squared, or not squared, cubed. Four divided by 3 times pi times our 125 e to the negative 10 to the third. So 8.18 times 10 to the negative 24 centimeters cubed. So this equals the volume of one chromium atom. Let's just write CR. Now what? Multiply by 2? Yeah, so we're going to have 2 per unit cell. So multiply this by 2. Or maybe I should say like this, times 2. And now that's 1.636 times 10 to the negative 23 centimeters cubed. And that's the volume of 2 chromium atoms. Is that the volume of the whole unit cell? No. So for the body-centered cubic unit cell is only 68% packing efficiency. So what does that mean? Yeah, so that number, really tiny number that we just calculated, is the volume that the 2 chromium atoms would take up in the whole unit cell. But the packing efficiency says that volume of the 2 chromium atoms is only 68% of the whole unit cell. So how would I calculate the volume of the whole unit cell? So if we think about it like this, because this is one of those calculations that I've always, in my head, has always been like hard to figure. So if it's the volume of the chromium over the volume of the unit cell equals the percent efficiency, and really, again, that wouldn't be the percent, that would be like the decimal proportion. Just rearrange this. So we have the volume of the chromium. So if we multiply both sides by the volume of the unit cell, divide both sides by the percent, then volume of the chromium divided by percent equals the volume of the unit cell. So we just have to take 1.636 times 10 to the negative 23 centimeters cubed and divide it by 0.68. And that's It's 2.41 times 10 to the negative 23 centimeters cubed. So that's the volume of a unit cell. So our 2 chromium atoms, because of the way that they pack together, take up that much volume. How much do those 2 chromium atoms weigh? Yeah. No, I think, were you saying, I think doing it that way would give us the mass of 2 moles. You're absolutely doing the right, you got the right idea. Start with this though. That's grams per 1 mole of atoms. 1 mole of atoms is 6.022 times 10 to the 23 atoms. Yeah. The right idea though. So this is the mass of 52.00. That's grams per 1 mole of chromium atoms. So if we want to convert that, that's 1 mole is equal to 6.022 times 10 to the 23 atoms. And that would give us the gram per 1 atom. And so we want 2 atoms. So we multiply this by 2 atoms. So we'll get 52 divided by 6.022 e to the 23 times 2. And so this is 1.727 times 10 to the negative 22 grams per 2 atoms. So now we can take that mass, which is the 2 atoms that fit inside a body-centered cubic unit cell, and then divide that by the volume of that unit cell. So I'm just going to bleed over onto this. 1.727 times 10 to the negative 22 grams divided by 2.41 times 10 to the negative 23 centimeters cubed. So that divided by that, and we get 7.177 or 7.818 grams per centimeter cube. Yeah. That is a problem that incorporates, I don't know, I like the way that incorporates the very basic thing of like how many atoms there are in a mole. All the way back. Does that make sense? I think if you can come back and, because there's a lot of steps to this problem, write out all those steps and make sure they all make sense. And I say that because that's exactly what I did when I tried to figure out this problem earlier today. If you can understand the why of each of the steps, like why am I trying to get to the volume of 2 chromium atoms? How does that help me get to the volume of the unit cell? And then using the molar mass to find the mass of 2 chromium atoms. This is just how many atoms are in the unit cell of the face-centered cubic structure. 4. So we've got the simple, if we want to abbreviate these things, there's the simple cubic unit cell. There's the body-centered cubic unit cell, and then the face-centered cubic unit cell. So this is going to have, the simple is 1, then it's 2, and then it's 4. So face-centered is the most atoms. Okay, and I believe that's it for math. The rest of this is like talking about how things pack together. So that's the unit cells. Unit cells are like the way to look at these larger crystalline structures in like a simplified format. How do we break this down into the smallest thing that we can talk about so that we can talk about that one thing and apply it to the rest of the crystal structure? Closest packed structures are really just a sort of different take at the same problem. And it's just the way that kind of maybe most relatable to how like spheres pack together. And we're changing our perspective here from looking at like, how can we talk about the smallest unit of atoms versus looking at individual, like how do layers stack up against each other? And these are related. The simple cubic structure is one layer of atoms in a square pattern with the second layer aligned exactly on top. So this is hard to see, but like these atoms here are all in the same layer. That's a layer, that's a layer. And so for each layer of atoms, there's another atom directly stacked on top of it. So you got these columns of atoms and rows of atoms all just stacked on top of each other. And it's not very efficient, right? We said that the simple cubic unit cell was only 52% efficient. What's a more efficient way that we could pack these? Not in terms of the other unit cells that we talked about. If you're thinking about if you want to get spheres into a box, you wouldn't stack them so that, or think about marbles, I guess, specifically. You wouldn't stack the marbles so the marbles were all directly on top of each other. That's not very efficient. Yeah, so if we offset them all so that the spheres sat in the little pockets made by each maybe triangle of spheres, all right, because this would be like one layer. And this is actually already changed so that the spheres are, right, they're offset. So we don't get perfectly straight rows. So the previous one would have been like this. But now we've taken one row and offset it by half, essentially. And now they can sit inside of those pockets, and we get better packing. Now, the way that we stack the next layer can change. So if we take our first layer, we stack a second layer on top, and we've essentially gone over a half and down a half and stack that layer on top, right? So now they're all sitting in those little gaps. Pretty satisfying. And then if we set another layer on top, there's a couple different things that we can do. So there's two different ones. Both have a packing efficiency of 74%. And they differ in the alignment of the third layer. So for layer A and our layer A, so for our first layer and our third layer, align. So if you were to draw a line through the top to bottom, they would all line up. That's one packing layer. That's the AB. And that's a hexagonal closest packing. So you get this sort of array that makes a hexagon in between those layers. And so you essentially can, if you expand this out a little bit, it's all hexagons stacked on top of each other. And if we expand this out a little bit, we've got this hexagon layer here, and then there's a triagonal layer underneath in between. So that's a hexagonal closest packing and a hexagonal unit cell. And then what we can change those, we can do an A, B, C. So layer A and layer C are now opposite each other. And both of these pack equally efficiently. And then this one is the one that's identical to the face-centered cubic unit cell. So we get four per unit. It's a little bit weird to look at here because they put it on this diagonal. So they take the blue ones here, red ones here, and then a green one. And if you set it on its side a little bit and then cut away to just one unit cell, we get that face-centered. So you end up with four atoms per unit. So we got a lot of different types of solids, and like the rest of this chapter is just talking about different types of solids. So like the things we've been talking about, so like crystalline solids, we can divide up into three different types. So we get molecular solids, so solids made of molecules, ionic solids, and then atomic solids. And then atomic solids are classified by the different types of interactions that hold them together. And so we're going to work through all of these in the rest of this chapter. Let's just talk about, see how far do I want to get here? Yeah, so like our molecular solids are solids whose composite units are molecules, ice, dry ice, anything made up of organic molecules. These are the ones that are going to depend mostly on the types of intermolecular forces. So you've got something like water, you get hydrogen bonding. The molecules are held together by those intermolecular forces. And then for those molecular solids, you can have a lot of different types. So these are different polymorphs of chocolate. So different structural properties. These first four aren't as great. So firm, but pore snap, sun blooming, melts in the hand. You get to polymorph 5, that's where you get a firm, good snap, smooth and shiny surface, melts in the mouth, most desirable. And then this last one, I believe, is what your chocolate turns into when you like leave it for a long time. So that Halloween chocolate that's been sitting since last year. It's just not very good. And then ionic solids are solids whose components are ions. So they're made up of different types of ions. And we're going to talk more about those. They have high melting points. Some general trends that we'll talk about there. And then atomic solids are those solids whose composite units are atoms. So xenon or iron or silicon dioxide. And those are the ones that we break up into further categories. The non-bonding atomic solids are like just noble gases. That's it. Nothing else is a non-bonding atomic solid. Very low melting points. That'll increase with molar mass. Atomic solids, where you've got metal ions in a sea of electrons. Lots of different variation in their properties because of varying bond strengths. And then the last one we'll talk about, and really just mentioning all of these, network covalent atomic solids, which are held together by covalent bonds. So diamond, graphite, silicon dioxide are all network covalent atomic solids. So like a diamond is actually a single, if it's a perfect diamond, it's a single molecule of carbon diamond structure. They're all connected. And then their crystal structures will be limited by geometrical constraints of the covalent bonds. So these are not closest packing structures. It's the angle of those bonds, and we talked about like Vesper theory and stuff, the angles that those bonds form at. We'll have very high melting points because covalent bonds are really strong. So what type of atomic solid would gold be? Metallic. It's a metal. And then of these three, which would you expect to have the highest melting point? Yeah, so this is going to be a non-bonding krypton, which is a noble gas. It's going to be a gas at room temperature. Iodine is going to be a molecular solid because it's iodine molecules, and then also just dispersion forces there. So then magnesium oxide is the only ionic solid, has the highest melting point. It's metallic. All right. That's all we're doing today.